Arunachalam sir, you are sitting in an auto?
Arun sir, you are traveling or what?
His mic is not working, it seems.
Roshan, are you okay?
I am fine, sir. I am fine, sir. I am better today.
Okay, good.
Sir, you are traveling in some, I think, legendary vehicle. It's amazing.
It is Ola vehicle. Yeah, I don't know.
Okay,
They are navigated like that. Right now, it is in Pune only.
I thought you have brought some special vehicle from Chennai itself.
Yeah, I ordered to BMW. Okay.
So you are here till which date, sir?
Friday.
Till Friday, okay. So you are coming to hotel. You are coming to hotel.
No, I'm going to supply end. No, I'm going to supply end. One more activity is there. So maybe at 9:30 only I reach hotel. That is why I told you, na. So my time was occupied with other people. So if time permits, I'll try to meet you.
No, it's very nearby. I will come at 10 to meet you. We'll have a tea. Don't worry.
Right. நான் கவனிக்கல ஜி அவனுக்கு கவனிச்சுட்டு சொன்னதை நான் பார்க்கறேன்.
Hello, good evening to all of you. Am I audible?
Good evening, sir. Good evening.
Yes, sir. Good evening, sir.
Good evening, sir.
Namaste, sir.
Good evening, sir.
Good evening.
Good evening, sir.
Good evening. Is my screen visible to you?
Yes, sir.
Yes, sir. Yes, sir.
Okay, fine. Please answer your reference. Aditya Kumar,
Present, sir.
Anand,
Present, sir.
Ananta Kumar,
Yes, sir.
Arunachalam,
Yes, sir. Present, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Present, sir.
Roshan Kumar,
Present, sir.
Sabish Kumar,
Present, sir.
Satish Kumar, Satish Kumar, Titus,
Present, sir.
Valish,
Yes, sir.
Vigneshwaran,
Present, sir.
Vijayaraj,
Present, sir.
Vikash,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj,
Present, sir.
Okay, so Satish Kumar is absent.
Sir, sorry, sir. I just connected a little bit late.
Okay, you have joined.
Yes, sir.
Thank you.
Thank you, sir.
Okay, welcome back. We are in chapter 2 of this course. We are discussing about thermodynamic aspects of combustion. Previously, we applied first law of thermodynamics and obtained two useful parameters. One is heating value, which is an estimate of thermal energy released during the combustion event. The second useful parameter we obtained is adiabatic flame temperature, which is a maximum temperature reached by the products of combustion under adiabatic condition. Both the parameters are obtained by applying first law of thermodynamics to the chemically reacting system. And we have discussed that both are very useful. Heating value is one of the important property of the fuel, and from the heating value we define an important performance metric, engine performance metric, which is called first law efficiency or thermal efficiency of internal combustion engine. So we also discussed about higher heating value and lower heating value. In the first law equation, you are supposed to use lower heating value because we never require latent heat of H2O in an IC engine combustion system. But what you measure by using an equipment, which is a bomb calorimeter, is a higher heating value. Okay, so you need to know how to convert this. We have discussed how to do that. And then adiabatic flame temperature is a maximum temperature reached by the combustion product. This is one of the important parameter that we need to note when we design the IC engine. It will help us to carefully choose the materials for the components. IC engine component, you know, because of the temperature, the components are subjected to thermal stress, and it's generally cyclic loading in IC engine. This is where it differs from gas turbine or any other external combustion based system. In external combustion based system, you will have a constant thermal loading. Here in IC engine, it is called cyclic loading. Cyclic loading means the engine is subjected to higher temperature only for a small period of time. And then again, it will be subjected to lower temperature. So temperature in IC engine system continuously varies. Nevertheless, we need to know what is the maximum temperature or theoretically achieved maximum temperature. Although it's a theoretical or a hypothetical value, we need to know that because we design engine with always some factor of safety, right? We need to know what is the maximum ideal temperature that will be reached by the system, right? That will help us to carefully choose materials so that the durability of the engine system is longer. Now, after this, I started a discussion on chemical equilibrium. So that is obtained by the application of second law of thermodynamics to the combustion event. So when we apply second law of thermodynamics to a chemically reacting system, we can come up with a concept called chemical equilibrium. Today, I'm going to discuss more about this chemical equilibrium. Before that, we need to know the composition of the combustion product because some of the combustion products are pollutants. Right, so we earlier discussed about combustion stoichiometry, which help us to find the product composition from the reactant. Once you know the reactants here in an engine combustion system are fuel and air. Fuel and air are reactant. Once you know the reactant fuel molecular formula, you'll be able to come up with the product composition by using this principal stoichiometry, wherein we relate reactants and products based on the conservation of atoms. Okay. So we could get the major species information from this principle, stoichiometric principle. But if the number of species in the product, combustion product is higher, this is not enough. Stoichiometric principle is not enough to get the product information. That's where the chemical equilibrium concept is useful. Okay, so it helps us to find the product composition if the number of species in the products are more. I will continue my discussion on that. Okay, so this is where I stop. So here, this concept chemical equilibrium is primarily applied to determine the composition of the combustion product. And as I said, this combustion product composition is a strong function of two parameters. One is fuel air equivalence ratio Phi, other one is temperature. And we already discussed how this equivalence ratio affect the combustion product. So we have considered three possible cases. One is stoichiometric case, where the major combustion product, I use the word major because these are the major species even in actual IC engine combustion. There are several minor products which we are ignoring here. Actual product composition is much more complex. Okay, it involves several other species. Generally, these three are the major species. That's why here with this simplified principle, we are finding out only the major species information. Under stoichiometric condition, you have only three major species, CO2, H2O, and N2, with phi greater than 1. Phi greater than 1 is fuel-rich condition. When you combust fuel-rich condition, you will have 5 product species. Apart from CO2, H2O, and N2, CO and H2 will also be there. CO and H2 are the products, major products of incomplete combustion. Because of oxygen deficiency, carbon burns to CO and hydrogen in the fuel comes out as it is. Okay, so these two are other species apart from the three major species when you go with fuel-rich combustion. With the fuel-lean combustion, apart from the three major species, you will also have oxygen. So you have 4 species, major species in the combustion product. So what we know from this analysis is Phi has a strong influence on the species that are present in the combustion product, major species that are present in the combustion product. Now let us look at how the temperature affects the product composition. And before that, when you have Phi less than 1, when you have fuel lean combustion, you have only 4 species, okay, in the product. Now, to find the number of moles of these 4 species, it is enough to go with stoichiometric principle, because with stoichiometric principle, you can form 4 equations, 4 atom balance equations, which is enough to find these 4 unknowns. Okay, and this is true only at lower temperature range as indicated here. At temperature less than 1250, 4 atom balance equations are sufficient to find these 4 unknown. What will happen at higher temperature when the temperature is above 1250, which is very well undergone by engine combustion system? The temperatures are much higher than 1250. At this higher temperature, what will happen? Dissociation reactions will happen. What are these dissociation reactions? Dissociation reactions are also classified as endothermic reaction. You know, chemical reactions are broadly classified into 2 categories. So one of the categories is exothermic. The other one is endothermic. What is exothermic and endothermic?
Exothermic, when the reaction occurs, it releases the heat, and whereas endothermic, we need heat energy to initiate the
yes. So these chemical reactions absorb thermal energy. Whereas exothermic reaction releases thermal energy. Okay, so exothermic combustion is exothermic. Any oxidation reaction is exothermic because it releases thermal energy. This is where we are interested to know about combustion. We are interested to recover the thermal energy and convert it into work in ICE system. Okay, so combustion as such is exothermic, but during combustion, there are endothermic reactions that happen inside the combustion system. And these endothermic reactions are strong functions of temperature. When the temperature inside the combustion system is high, these reactions happen. So what will happen under these conditions? The species which are very stable will absorb thermal energy and start to dissociate. Okay, the species which are very stable at lower temperature will absorb thermal energy at higher temperature and start to dissociate, which is an endothermic reaction. 2 important reactions, endothermic reactions, are indicated here, which happens in IC engine combustion system. CO2 will dissociate and form CO and oxygen. H2O dissociate and form H2 and oxygen. Okay, so this is called CO2 dissociation reaction. Second one is H2O dissociation reaction. Okay, basically the stable molecule, CO2 molecule, disintegrate and form CO and O2. Similarly, stable H2O molecule disintegrate and form H2 and O2. This reactions happens at high temperature as indicated here at temperatures well above 1250. these molecules will disintegrate and form additional species. Okay, so you will have COH2 present in the combustion product, although you are combusting under fuel lean condition. You know what a fuel lean is. When I say fuel lean condition, it's an oxygen rich condition. Okay, even with more oxygen, you have CO and H2 present in the combustion product. We have already considered that CO and H2 are the products of incomplete combustion, isn't it? So incomplete combustion happens when there is a deficiency of oxygen. This is what we discuss here. With the deficiency of oxygen, incomplete combustion happens and CO and H2 will appear in the product. But now what is happening? Even with fuel lean or oxygen rich condition, I have this incomplete combustion product CO and H2 present along with the other major species. Okay, this happens not because of oxygen deficiency. This happens because of dissociation reaction of stable species, which is what we categorize it as endothermic reaction. Stable molecule disintegrate and form additional species. Since CO2 and H2O are present in major amount in the engine exhaust, they can very well form CO and H2 by undergoing dissociation reaction by absorbing thermal energy. Okay, so the point for you to note down here is when P is less than 1, that is fuel lean or oxygen rich, at higher temperature, T greater than 1250 Kelvin. This is a threshold value determined based on experiments. Okay, people observed based on experiment that at this higher temperature, you are going to have dissociation reaction from major species present in the exhaust, which are CO2 and H2O. Now, under this condition of P and T, you could now count the number of major species present in the engine exhaust. So you have CO2, H2O, CO, H2O2, and N2. You have 6 unknowns. Now I need to find the number of moles of all these 6 species present in a major amount in the engine exhaust. Now, in order to get these 6 species, you cannot get the number of mole information only by stoichiometric principle, because we know that we can form at the most only 4 equations from atom balance by applying stoichiometric principle. But how many unknowns I have? I have 6 unknowns. So stoichiometric principle alone is not sufficient to find the product composition under these conditions. Okay, even with fuel lean, when the temperatures are more, I am going to get more additional species, major species. So stoichiometric principle has a limitation. That is what is highlighted here. Now, how do I find the product composition? To find the product composition, I need to now apply chemical equilibrium concept. With chemical equilibrium concept, you can form additional equations by using those equations. Okay, apart from the 4 atom balance equation, you will be able to find the product composition. Okay, this is the usefulness of this chemical equilibrium concept. Having understood the background information about how useful this concept is, now we are dwelling deep and we are going to discuss what this chemical equilibrium is. How can I form additional equations by applying this concept? So chemical equilibrium, as indicated here, it provides a reasonable first approximation to compute composition of combustion products at high temperature. When the temperatures are high, dissociation reactions are going to happen. More number of species are going to form in the combustion product. So we need to apply this concept. There is no other way you can find the product composition. Now, what this chemical equilibrium is? Okay, we know that when a chemically reacting system is under chemical equilibrium, the rate of formation of any species, say I, is equal to rate of consumption of that same species. Okay, the rate at which the species I is formed is equal to the rate at which the species I is consumed. So there is a formation, there is a consumption. Okay, at the equilibrium condition, the rate of formation is equal to rate of consumption. So what it means to me, there is no net change of species I. There is no net change of species I. Under equilibrium condition, there is no net change of species I. Because the rate of formation of that species is equal to rate of consumption of species. So this is a qualitative or physical meaning of what an equilibrium condition is. An equilibrium condition implies that there is no net change of any species in a chemically reacting system because the rate of formation and rate of consumption of that species, it remains the same. Okay, this is the physical meaning of chemical equilibrium. Now this is only qualitative understanding. This is not enough. Now we need to give some equations and establish the conditions for chemical equilibrium so that we can get the product composition. That is our focus, right? Now moving ahead, we are going to discuss about the conditions for chemical equilibrium. To establish the conditions for chemical equilibrium, we are going to apply first and second law of thermodynamics. This is where the principles of thermodynamics comes into the picture. We are going to see how we can establish conditions for chemical equilibrium in order to get a quantitative estimate of product composition. Okay, from that we will see how we can form additional equations. So for applying thermodynamic principle, you know it's a steady state approximation. So we will consider a steady state and apply this principle so as to arrive at the condition. This is what we are doing here. Now we are considering a chemically reacting system. When I say system, I already defined what a system is. It's a fixed mass of matter. When I say chemically reacting system, the fixed mass of matter include fuel and air, which can react chemically, which can undergo chemical reaction. This is what I mean by a chemically reacting system. Now let us consider a chemically reacting system at a pressure P and temperature T, because I'm going to apply thermodynamic principle. I'm considering the steady state approximation here. For a chemically reacting system at this pressure P and temperature T, with the application of first law of thermodynamics, since pressure remains at P, I can write del Q is equal to dH. This is from first law. So you know change in heat interaction is given by change in enthalpy when the pressure remains constant. This is according to the first law of thermodynamics. Now, you know, first law of thermodynamics just relate heat and work, but it doesn't give you how much of heat can be converted to work. This is where the second law of thermodynamics comes into picture. It provides you an estimate of how much of heat can be converted into useful work, how much of energy is unavailable. This unavailable form of energy is defined through the term entropy. Okay, so by second law of thermodynamics, you can write del Q less than or equal to TdS. Okay, this is from change in entropy equation. Change in entropy equation is you know ds can be greater than or equal to del Q by T. ds will be equal to del Q by T if the process is reversible, ideal. When the process is irreversible, ds will be greater than del Q by T. Okay, that's why it is written as del Q less than or equal to TdS. Okay, ds is change in entropy, which provides an estimate of unavailable form of energy. Okay, that is available for conversion to work. So this is according to second law. Now when you combine this first and second law, you can write this equation. So here del Q is replaced with dH. You can write it as dH less than or equal to TdS. Okay, if you rearrange this equation, you can write it as dH minus TdS less than or equal to 0. Okay, and this is for a small change. You see the notations here. I have used D for H and del for Q. Can anyone tell me the notations are different for different parameters? So what could be the reason? This is according to the standard representation that we follow in thermodynamics. Why do we use D for H and del for Q?
So enthalpy change is small in that sense. When there is a progressive change in that way, and del Q is basically amount of total energy that is changed in that way. So probably have used the delta.
No. My question is, this is a smaller change. We use the word infinitesimal change. Infinitesimal is very small change. Okay, that's why we use D or del. But my question is, why do we use del for Q and D for H?
Sir, Q is quasi-static, so it happens that way. So that's the reason why del we are using.
Quasi-static.
No, sorry. Because H is the function of P into D, P dV, sir, in that way.
Okay, have you come across Moyne function, path function?
Heard, sir, but forgot. Sorry.
So Q is actually a path function. Q and W are path function. Okay, they are non-property. H, enthalpy, is a property. Okay, so properties are point function. They doesn't depend on a path followed by a process. Okay, whereas properties see Q and W depends on the path followed in a process. They are called path functions. Whereas properties like H, okay, enthalpy, they are called point function because they are independent of the path followed in a process. They depend only on the state. Okay, they do not follow the path followed in a process. That's why to distinguish a point function and path function, you have different notations here. For H, we use D, okay, and for Q, we use del. Now, when you combine this, you can write it as dH minus TDS less than or equal to 0. For a finite change, this is the previous equation. This equation is for a smaller change, infinitesimal change. Now, for a finite change, you can rewrite this equation as delta H minus T delta S less than or equal to 0. Now, this delta H minus T delta S is replaced with the term delta G, that is less than or equal to 0. What is this G? G is called Gibbs free energy. G is equal to H minus Ts. G, Gibbs free energy, is a measure of chemical potential. A chemical reaction will proceed as long as a chemical potential is available. Now, how a fluid flow happen? How a fluid flow happen?
Because of a gradient.
Pressure gradient.
Pressure gradient. How the heat transfer happen?
Because of different temperatures.
Temperature gradient.
So whenever there is a pressure gradient, the fluid flow is going to happen. Okay, whenever there is a temperature gradient, heat transfer is going to happen. Okay, these are natural processes. Similarly, whenever there is a gradient in the chemical potential, whenever there is a change in Gibbs free energy, the chemical reaction is going to happen. Okay, chemical reaction will proceed whenever there is a change in chemical potential or gradient in chemical potential. If it is available, a chemical reaction will proceed. So your physical meaning of this is, reactants are converted to products. Okay, as long as the energy is available with the reactant, the chemical reaction is going to proceed. When all the energy is consumed, the chemical reaction cannot proceed. Now, at a chemical equilibrium condition, the change in Gibbs free energy will be equal to 0. Remember that we have started this derivation for a chemically reacting system at a pressure P and temperature T. That's why I'm writing the condition for chemical equilibrium as delta G is equal to 0. What it means, there is no change in Gibbs free energy, meaning that there is no chemical change in chemical potential, or there is no gradient of chemical potential available for a chemical reaction to proceed. So now you can say that the reaction, chemical reaction, is under equilibrium condition. Okay, so del G can be less than or equal to 0 at equilibrium, chemical equilibrium. Del G will be equal to 0. This is a condition for chemical equilibrium that we get based on first and second law of thermodynamics. Now, moving ahead, we are going to consider a chemical reaction and see how this equation can be expanded. So here we are considering a general chemical reaction, small a capital A plus small b capital B. These two are reactant species. Capital A is one of the species, capital B is another species. The small a and small b stands for stoichiometric coefficients of species A and species B. I will give more details about this in the next topic, which is on chemical kinetics. Now here our focus is to see how we can apply this chemical equilibrium concept to form additional equations to get the product composition. So for a general chemical reaction involving these four species, A, B, C, and D, A, B, C, and D are the species which are involved in the chemical reaction. Okay, and small a, B, C, D, these are the coefficients, stoichiometric coefficients of these four species. The reaction proceeds in a forward direction with the rate constant K with the subscript F. Again, I will talk about this rate constant in more detail in the next topic on chemical kinetics. So reaction proceeds in a forward direction, okay, with the rate constant Kf. The reaction also proceeds in a reverse direction with the rate constant Kb. So this reaction is proceeding in forward as well as backward direction, and the associated reaction rates are indicated as Kf and Kb. Now I want to find the net rate of reaction progress. The net rate of reaction progress is given by Q dot R is equal to Kf with the square symbol A. A is enclosed in a square symbol. The square symbol stands for concentration of a particular species. The square symbol stands for concentration of a species. Again, I will give more details in the second topic, which is on chemical kinetics. Okay, I will give more information about this. So, Kf, concentration of A raised to the power A, B raised to the power small b. So this is the rate at which the reaction proceeds in the forward direction. Okay, so physical meaning of this is a chemical reaction proceeds in a forward direction based on the concentration of A, its stoichiometric coefficient, concentration of B, its stoichiometric coefficient, and then there is something called rate constant, which is a constant which will decide how quickly a chemical reaction proceed in a particular direction. Okay, so this is in forward direction and this is in backward direction. So you are finding net rate of reaction progress. That's why you are subtracting this reverse reaction from the forward reaction. Okay, the rate at which the reaction proceed in the reverse direction is given by Kb, which is a rate constant for the reaction to proceed in the reverse direction, multiplied by the concentration of the species C and D raised to the power stoichiometric coefficient. This is the net rate of reaction progress. Okay, now under equilibrium condition, chemical equilibrium condition, the rate at which the reaction proceed in the forward direction will be equal to the rate at which the reaction proceed in the reverse direction. So this and this will be same. So you can say that Q dot R is 0 at chemical equilibrium condition. Okay, so then you can write this equation Kf by Kb is equal to concentration of Cd raised to the power stoichiometric coefficient in the numerator. The denominator you will have concentration of AB raised to the power stoichiometric coefficient. Okay, this Kf by Kb is defined or replaced using another constant, which is K with a subscript C. This constant K with a subscript C is called equilibrium constant based on concentration. Equilibrium constant based on concentration, because this equation is written based on the concentration of the 4 species involved in the chemical reaction. Another useful form or equivalent form of this is Kc is now replaced with Kp. Here you could see that the concentration are replaced with P with a subscript C raised to the power stoichiometric coefficient. Similarly, you have a partial pressure of other species raised to the power stoichiometric coefficient. This P stands for partial pressure. Okay, PC is partial pressure of species C. Okay, these two are equivalent forms of the same equation. One is based on concentration, the other one is based on partial pressure. Why we want this equation carries significance? Because you can expand this partial pressure in terms of mole fraction. We want to form additional equation to get the information about the moles of major species in the combustion product. Okay, that's why we have written an equivalent form of Kc equation in terms of partial pressure, because this partial pressure can be expressed in terms of mole fraction. Can anyone tell me how I have obtained this equation? How I have obtained this equation from this equation? The previous equation you could see that it is written in terms of partial pressure. The next equation, equation 3, is written in terms of mole fraction of the same species.
So basically, sir,
So partial pressure is concentration into total pressure. Means
Concentration or mole fraction?
mole fraction.
Okay,
Basically-
so can I write a general form as Pi? I stands for any species. That is equal to Xi into P. P is total pressure, Pi is partial pressure, Xi is mole fraction. So this is mole fraction. What is this law? This is some law, right? Pi is equal to Xi into P.
Sir, Avogadro law, if I'm not wrong.
This is Dalton's law.
Oh, that is
Dalton's law of partial pressure. So from Dalton's law of partial pressure, you can relate partial pressure with the total pressure through the mole fraction of a particular species. Okay, that is how we obtained this equation from the previous one. Partial pressure of the 4 species are expressed in terms of mole fraction of the 4 species raised to the power stoichiometric coefficient multiplied by total pressure. Okay, here in the exponent you will have C and D. Okay, this is in product, you are just adding it, and A and B are in the denominator. It is in the division, so you are subtracting it. So P raised to the power C plus D minus A minus B. This is what you will get by applying Dalton's law. Okay, you can convert this partial pressure into mole fraction. This is what our interest is, because we want to find the product composition having applied the chemical equilibrium concept. By using this concept, we want to find the product composition. So we have first written an equation for a general chemical reaction in terms of rate constant based on concentration, and then we have taken an equivalent form, rate constant or equilibrium constant based on partial pressure. Okay, from partial pressure, we have moved on and get mole fraction of the species which are involved in the reactions. This is under equilibrium condition. So this constant, rate constant, is referred to as equilibrium constant because we are considering chemical equilibrium conditions. Okay, so that K will be equal to Xe raised to the power C. Similarly, you have other three species that are participating in the chemical reactions. You can also write this Kp in terms of another equation. Kp log to the base E is ln. Ln is log to the base E. Ln Kp is equal to minus delta G with the circular symbol. The circular symbol stands for standard condition. I already defined what the standard condition is. This is at 1 atmosphere and 25 degrees Celsius. That is what is the standard condition. We consider 1 atmosphere pressure, 25 degrees Celsius temperature. That is what this circular symbol means. Log to the base E Kp is equal to minus delta G circular symbol divided by R bar T. R bar is universal gas constant. This is a constant value. Temperature is known to you. This delta G can be obtained from standard thermodynamic table for important chemical reactions. So this is known to you. This is known to you. This is known to you. From this you can get this Kp value. Okay. From this you can get Kp value. There is a derivation behind this equation connecting Kp and delta G. I have skipped that. It is not important for you. I have written the final form of the derivation here. So initially we obtained an equation for Kp in terms of mole fraction. Now we have written another equation for Kp in terms of delta G, R bar and T, which are known information. From this known information, you can get the value of Kp. Once you have the value of Kp, you are expressing Kp in terms of mole fraction of the product, combustion product. So it means you can form an additional equation with a known Kp value. That is how you will be able to get the product composition by applying this chemical equilibrium concept. So I have demonstrated that here. Here we are going to see how we can apply that to get an additional equation, application of chemical equilibrium concept to compute composition of the combustion products. So to do that, I have considered fuel-rich hydrocarbon combustion. Simplest case I have considered here, fuel-rich hydrocarbon combustion. You know, for fuel-rich, what will be the value of Phe?
More than one.
More than one, sir.
Yes, so Phe is greater than 1 for a fuel-rich hydrocarbon combustion. I'm writing it in the general form, which we have already discussed. So C alpha H beta. Alpha stands for number of carbon atom, beta for number of hydrogen atom. That will be added with, so this is fuel, hydrocarbon fuel, and this is air, O2 plus 3.76 N2 multiplied by alpha plus beta by 4. What is this alpha plus beta by 4? What is this coefficient? Yes.
Number of atoms, if I'm not wrong. Scalar.
Stoichiometric, if you write stoichiometric combustion equation, this won't be there. 1 by Phe won't be there. You will have C alpha H beta plus alpha plus beta by 4, right? This is stoichiometric coefficient. So now, since we are considering fuel-rich combustion, I need to consider the effect of Phe. So you are multiplying stoichiometric coefficient with 1 by Phe. If at all it is stoichiometric condition, what will be the value of Phe?
It will be 1, sir.
Phe will be 1. So you will have an equation written as C alpha H beta plus alpha plus beta by 4 O2 3.76 N2. That is nothing but stoichiometric combustion equation. Now to consider the effect of Phe, because I am not considering stoichiometric combustion, I am considering fuel-rich combustion. That's why I have 1 by Phe multiplied with alpha plus beta by 4. Is it clear? So with this, yes, with this, you will get this major species. So since it is a fuel-rich combustion, you will have CO2, you will have CO, you will have H2O, you will have H2, you will have N2. How many species are there? Major species are there? You have 5 species. Now I want to know the number of moles of these 5 species. Well, how many equations I can form by doing atom balance?
It will be 4, sir. It's 4.
4 equations I can form from atom balance. So that is not enough. So I need to form one more equation because I have 5 unknowns here. So 4 equations are not sufficient. I have 5 unknown. That additional equation I'm going to form by applying chemical equilibrium concept. So you will have 4 plus 1 that is sufficient to get this 5 species information. Okay, that is what we are going to see here by considering a fuel rich hydrocarbon combustion that leads to 5 major species N1 to N5. So I can form 4 equation. Now I need to form an additional equation. To form an additional equation, you are going to apply chemical equilibrium concept. To apply chemical equilibrium concept, what you should do is you should consider additional chemical reaction involving any of these species. So you have 5 species in the product. These species, as I have already informed you, they will also participate in other chemical reactions, right? So now the reaction, chemical reaction I have considered here is called water gas shift reaction. This is one of the prominent reaction that happens in IC engine combustion. Water gas shift reaction, which is CO2 plus H2, forms CO and H2O. It happens in forward as well as in the reverse direction. Okay, this reaction, water gas shift reaction, as you could see, it involves 4 of the species that we have considered here. You have CO2, you have H2, you also have CO, you also have H2O. This is one of the reactions that happens in IC engine combustion at high temperature when you have a fuel rich combustion happening at high temperature. This is an additional reaction that can happen. Now I have written this additional reaction. Now I am going to apply the chemical equilibrium concept and form one more additional equation. Okay. So this choice of this particular chemical reaction is your choice actually, but you have to carefully choose in such a way that it involves most of the species present in this general equation which you have written. So I have chosen this equation because 4 of the species participating in the general equation are involved in the water gas shift reaction. Okay. So now what I will do, I am going to treat this equation in comparison to what we have discussed earlier as a generic chemical reaction. A moles of species A with B moles of species B form C moles of species C plus D moles of species D. And from this I have written Kp, equilibrium constant, is equal to Xc raised to the power C, Xd raised to the power D divided by Xa raised to the power A, Xb raised to the power B. And this is mole fraction. This is multiplied by total pressure raised to the power C plus D minus A minus B. What you have to do is you have to just compare this generic equation with the specific equation you have considered here. Okay, generic and specific. This is a general chemical reaction and associated Kp equation. This is a specific chemical reaction you have considered now, and this will be the associated Kp equation. So Kp can be written as, so here Xc raised to the power C. Okay, so this is species A, this is species B, species C, this is species D. Now what is the stoichiometric coefficient here in this chemical reaction? So small a, b, c and d?
1.
1. So you have 1 here, 1 here, 1 here and 1 here. Okay, so now you compare these 2 forms. Okay, I am writing the equation for Kp. That will be Xc. What is Xc? Mole fraction of C. Mole fraction of C can be written as number of moles of C divided by total moles. Now, how many moles? What is species C here? This is species C, right? CO is species C. How many moles of CO is present in the combustion system? Now you have to go back to the original equation. How many moles of CO is present in the combustion system?
1.
N2.
N2 moles of CO is present. Stoichiometric coefficient is 1, but in the combustion system, you have N2 moles of CO available. So it will be, equation will be N2 by total moles raised to the power small c. Small c is stoichiometric coefficient, which is 1. That is multiplied by Xd. What is Xd? Mole fraction of D. What is species D? H2O. How many moles of H2O are present in the combustion system?
N3.
N3 moles. So this equation will be N3 by total mole raised to the power small d, which is stoichiometric coefficient, that is 1 here for H2O, divided by Xa. What is Xa? Number of, mole fraction of species A. What is species A here? CO2. how many moles of CO2 are present in the combustion system?
N1.
N1 moles. So N1 by total mole raised to the power small a is stoichiometric coefficient, which is 1 here. Then multiplied by XB, which is mole fraction of B. What is species D here? H2. How many moles of H2 are present?
N4.
So you will be having N4 by NT raised to the power small b. Small b is 1. Okay, so this is what will be the Kp equation. N2 by Nt raised to the power 1, N3 by Nt raised to the power 1, N1 by Nt raised to the power 1, N4 by Nt raised to the power 1 multiplied by total pressure raised to the power C, small c plus d minus small a minus small b. So you know all are 1 here. All the stoichiometric coefficients are 1 here. So p raised to the power 1 plus 1 minus 1 minus 1. What is this value? P raised to the power 0. What is p raised to the power 0?
1.
So this will be 1. So and N2, Nt total mole is there in the numerator as well as in the denominator. That will get cancelled out. The final equation you will get is Kp is equal to N2, N3 by N1, N4. Here N2, N3, N1, N4 are unknown, but what is known to you? Kp is known. You can write Kp in terms of del G by R bar T. Del G for water gas shift reaction is available in the thermodynamic table. So this is known, R bar is known, T is known. From this you can get the value of Kp for water gas shift reaction. So this is known to you and you have this unknown. This is equation number 5. You already have 4 atom balance equation from stoichiometry by balancing the atoms on the reactants and product side. So you have 4 atom balance equations. You have one more equation now based on the consideration of chemical equilibrium concept. With these 5 equations, you will be able to get the 5 unknowns. Okay, so you have 4 atom balance equation, 1 chemical equilibrium based equation. Solving this, you will be able to get N1 to N5, which is nothing but product composition. So you are obtaining product composition, okay, with more number of species. Here I have considered the simplest case wherein I have 4 plus 1 case. Similarly, you can write additional chemical reactions and form additional equations involving Kp, and thereby you will be able to get the product composition. So whenever there are more than 4 species in the product, combustion product, you have to apply chemical equilibrium concept, form additional equations using those. By solving those equations, you will be able to get the information about the product composition. Okay, so this is the usefulness of this concept of chemical equilibrium, wherein we can get information about the product composition in a complex system where the number of species are more than simple stoichiometric principle can provide. Clear?
Sir, one query. Can I answer, please? If you
Yes.
Well, basically, the generic equation that we have given for the fuel-rich hydrocarbon combustion is C alpha plus H beta 1 upon phi and like that. Now we have considered a secondary equation, which is water gas shift equation. Now, while doing the equilibrium balance for this equation, sir, also we have considered the what I mean to say, like molar mass, molar content is like 1 coefficient like that, but N2 is taken from the above equation. I just got a little confused in this. Why the molar fraction of first equation has to be considered in this equation?
So I'll give more detail about this. It's a good question. I'll give more details about this in the next topic on chemical kinetics. So this is a generic equation, right? And the second equation we have written is called elementary reaction. There is something called global chemical reaction and elementary reaction. Elementary reaction will always proceed with stoichiometric coefficient. This is an elementary reaction. And what you have written in the beginning is a general reaction, which is also called global reaction. So you have a global reaction and this unknowns N1, N2. I have used some generic notation N1, N2, N3, N4, N5 because they are unknowns. Okay. And these species that we are considering in the generic equation are undergoing additional reactions. Those additional reactions are categorized as elementary chemical reactions. Elementary chemical reaction proceed only with stoichiometric coefficient. I have so many moles of the CO2, CO, H2 and H2, and these species are participating in other elementary reaction only with stoichiometric coefficient. Do you understand? I have these many moles of these 4 species available in the combustion system, and these species are participating in some other reaction categorized as elementary reaction, but that reaction will proceed only with stoichiometric coefficient.
Thank you, sir. Thank you so much.
Yeah, okay.
Thank you, sir.
Fine. Any other doubt? So with this, I conclude this concept of.
Sir,
Yeah, go ahead.
sir, so in that case, NT for equation we have written that NT is N1 plus N2 plus N3 plus N4 plus N5, right? Or
No. NT here I am considering in the elementary
elementary reaction. Okay, sir. Okay, sir.
elementary reaction, chemical reaction. I have some total moles of those species which are categorized as N1, N2, N3, and these species, whatever I am considering in the general equation or global equation, chemical reaction, is undergoing some other categorized as elementary. Elementary reaction will always proceed with stoichiometric coefficient.
Okay, sir. Understood. Sir. Thank you.
Like I have started the discussion with the dissociation reaction, right? Dissociation reactions are elementary reactions. CO2 forms CO and H2. You can also consider those reactions. The reason why I have considered the particular chemical reaction I have shown to you is it involves 4 of the species, unknown species in the product. That's why I have chosen water gas shift reaction. Okay.
Sir, so in case of C is equal to 1, where the number of products is 3, whereas the atom balance equations will be 4. So, means will there be the consistency of those?
It's not a problem. You can form more than what is required. So
Okay.
the purpose here is to get the unknown. It doesn't matter if you have more equations. You'll be able to get the unknown, right? The objective here is to get the unknown. That's it. If you have more, it doesn't matter. It's not a problem. But if you have insufficient number of equations, that is why the problem started. This is the reason why we have taken this concept, chemical equilibrium concept, because I have an insufficient number of equations.
Yes, sir.
Okay.
Sir, one more question, sir. If we have one more unknown, like if we had 6 unknowns, so we
You
have
have to, you have to form one more additional equation with Kp. To form that equation, you have to consider additional chemical reaction.
okay, sir. And that equation we can choose based on our convenience. Here we have chosen one water shift equation because it is convenient and means shorter reaction, so means smaller reaction. So we can choose accordingly, right, sir?
Yes. You can choose any chemical reaction. It's your choice. Once you carefully choose a chemical reaction involving many variables that you have in the original equation, it will help you.
Understood, sir. Thank you, sir.
Okay. So with that, we have now moved to the last topic. I will just provide an overview of this last topic and continue this in the next class. So we have now moved on to chemical kinetics. Whatever we have discussed so far here in thermodynamics of combustion is based on the application of thermodynamic principle, and I already started this chapter with a note on why we need to consider such an approach, and this approach is steady state based approach, steady state approximation. Nevertheless, it provides very useful information about combustion event because we can get product composition, we can get heating value, we can get adiabatic flame temperature. Just now we discussed about chemical equilibrium, which will provide us more product composition, right? some of the products are pollutants. So we need to know the number of moles of those products which are formed from combustion. This is the usefulness of this concept, thermodynamic concept. Although it is a steady state approximation, it provides very useful information about the combustion event. But the shortcoming of this approach is it provides only steady state information. And you know, combustion is not all about only steady state. It also involves transient. What is transient? Time-based information. What is missing in thermodynamic aspects? Time-based information you cannot derive. Right? That is where chemical kinetic comes into picture. It provides you transient information about the combustion event. What is transient? Time-based information. What is the time-based information you need to know? What is the rate at which the thermal energy is released? Rate at which the thermal energy is released means you are getting thermal energy release as a function of time. This is one of the useful information you need to know when you do analysis of the combustion event in IC engine. You need to know the rate-based thermal energy release, not the gross release. So what you get from first law equation is only gross thermal energy release. But what is more important is the rate at which the thermal energy is released, because in the engine cycle time, once you know the rate at which the thermal energy is released, you can time the thermal energy release appropriately so that you can maximize your engine power output or torque output. Okay, this is one of the vital or critical information. We need to know the time-based thermal energy release. Similarly, we need to know the time-based consumption of reactant and formation of product, because some of the products are pollutant. If you have to devise a pollutant mitigation strategy in the sense pollutant reduction strategy, you need to know the rate of formation of pollutant, at what time in an engine cycle the pollutants are forming, okay, and at what rate. With respect to time, how the pollutant concentration is changing. I need to know that information. Without that, I cannot devise a suitable pollutant control strategy. So what is missing here in thermodynamic aspect? Time-based information is missing. That information will be filled in if we know the chemical kinetics. So this is where we are going to discuss about this topic on chemical kinetics, which provides us time-based or transient information about the combustion system. I stop here. If you have any questions, you can ask.
Sir, you mentioned about controlling the products like that emissions. So when we talk about emissions, like emission control in the sense of ignition control, right, sir? Like we have to control the ignition.
Emission control in the sense that there is an in-cylinder emission control and after treatment control. In-cylinder control is reducing the pollutant level within the cylinder itself. Until otherwise, when the pollutants are forming at what rate, you cannot devise a suitable method to reduce the pollutant formation inside the cylinder itself.
Okay, sir. Understood, sir. So ultimately, we will control the ignition in such a way that the pollutions are formed suitably.
Yeah. So that is one of the external control that you can do. You control the timing of combustion, startup combustion. That will help you to phase it appropriately. That will help you to reduce or mitigate the formation rate of pollutants. So you have to time it properly. You have to time thermal energy release properly. You have to time it in such a way that the pollutant formation levels are reduced. Suppose if you retard fuel injection timing, the NOx formation is going to reduce. I will talk more about it in the second module. But here, when we delay the start of combustion event, you know that the combustion temperatures are going to drop. With a drop in combustion temperature, you can reduce the NOx level, oxides of nitrogen level, because that is highly sensitive to temperature.
Understood, sir. Thank you.
Okay.
It was very engaging, sir.
Sir, in line with the same discussion what we had just now, in case of dissociation, let us say CO2 dissociation or H2O dissociation, when there is a very high temperature in the combustion chamber, when gases expand, means basically during exhaust stroke or maybe after valve opening, that dissociated products will go back to the original reactant. It means, for example, CO and O2 will react and go back to CO2. So it will again be an exothermic reaction. So if it
happen as easily as you are thinking, because these reactions will freeze. We use the word frozen. Okay, so these chemical reactions freeze. Generally, they happen at a very high temperature, the dissociation reaction, and then get frozen during the later part of expansion stroke. It won't continue in your tailpipe. That is what you are asking, right? If the reverse reaction happen in the engine tailpipe, I'm going to get higher temperature. Is that correct?
Yes, sir. Yes, sir. That is
What I'm saying is the reaction will be frozen in the expansion stroke itself. This won't continue in the tailpipe.
Okay, sir. Yes.
The reaction will get stopped there itself. It won't continue for a longer period of time. Only few chemical reactions will continue with the very low molecular weight hydrocarbon. Hc oxidation is something that happens. It may happen even in the tailpipe, because even at lower temperature, that oxidation reaction will continue to happen. I will talk about that in the second module. But these endothermic reactions will get frozen in the cylinder itself.
Okay, sir. Thank you.
Fine. So it's time up. I stop here. I will continue it on Monday. Thank you.
Thank you so much, sir. Thank you so much.
Thanks a lot, sir. Thank you.
Thank you. Bye.
Thank you, sir. Have a nice week ahead, sir.
Thank you. Bye.